So this is what's called the chessboard problem, and the idea in the chessboard problem is that the king wanted to reward the person who invented the game of chess. So the fellow who invented it said, okay, I'd like you to put 1 grain of rice on the first square. He wanted rice for his payment. And he said, on the second square, I want you to double that and put 2 grains. On the next square, I want you to double the 2 and put 4. On the next one, I want you to double that and get 16. So there's only 64 squares on the chessboard, and this seems like it wouldn't be such a bad deal, but you find out that it's quite a bit of rice. In fact, more rice than the entire world, and sometimes this problem goes on, even computing how many swimming pools worth of rice it would be and how far around the world world would be covered with rice if this happened. So it's quite a good illustration of how fast exponentials increase. So now we need to write the equation describing the situation, and there's 2 ways to write it. Well, the classic way to write an exponential equation, and this is exponential because it's doubling, is you say the amount you have is the amount at times 0 times 2 to some exponent. And if I let the exponent be n, then in order to get a0 at the right time, I have to let n vary between 0 and 63. Or if I don't want to start with 0, I would have to, this is a at times 0, of course, times 2 to the n, and now n can vary between 1 and 64. So it just depends on whether you want to number your chessboard starting with 0 or starting with 1. So there's your equation. And now, what is a0? He was supposed to put 1 grain of rice, so this is really 1, and so that's, you have a pretty easy problem. Or simple rather, is 2 to the n. Now the question is, on what square, that means for what value of n, does the king have to put 1,000,000 grains of rice? So 1,000,000 is 10 to the 6. So I put the 10 to the 6 here, equals 2 to the n, and this is just an inverse problem like you've done before. You need to get the n down onto the main playing field here. So to do that, you take the logarithm of both sides. The easiest log to take in this case is log. So you've got the log of 10 to the 6 on this side equals the log of 2 to the n on this side. The 6 comes out in front, and log 10 is 1, so this is just 6. Alright, that's easy enough. And over here, whoops, I have an n log 2. Log 2 is a button on your calculator. It's 0.3010. You divide 6 by that number and you find out n. And n would be the square on the chessboard the king would be supposedly having to place 1,000,000 grains of rice. After doing all the projectile problems in 105, now at least you get to add terminal velocity. Because if you don't add air resistance to a problem, when you shoot an arrow into the air, it comes back down with the same velocity that it left the bow, which, as we know, is not realistic, and we're glad of that. Okay, so here we have a falling body, say a skydiver, or even an arrow coming back down from the sky, starting at whatever height it turns around, and it comes back down, and this equation describes its behavior. Now, you don't have to derive this equation, you just have to look at it and understand it. And most of it, what it requires is putting the numbers in the equation and observing where it's going to go, what's going to happen. All right. So that's what the first step is. T equals 0. In other words, what's the initial velocity of this body? So I put t equals 0 in the equation. What do I get? I've got a 50. 1 minus e. Well, 0 times negative 2t is just 0. Right? I've got 50. And what's anything to the 0 power? It's 1. 1 minus 1 is 0 times 50 is 0. It starts off with a 0 downward velocity. And now again, I want you to think of what happens to these equations as t gets really large. And okay, look at this equation again. There's no t here, at least you can't see it. Okay, 50, none. Just a number. 1, just a number. The only thing that's affected by t is this last term out here. And how does it behave with t? This is a negative sign. The negative sign on an exponential makes it a decaying exponential. So I'm going to graph this thing. It's going to start at 1, and it's going to go down like this and head out towards 0. So as t goes to infinity, as t gets very large, if you don't like that way of talking, as t gets very large, e to the negative 0.2t, however you scale it, that goes to 0. So what happens? This term goes to 0, and what are you left with? 50 minus 1, which equals 50. So this is your terminal velocity. The skydiver starts with a downward velocity of 0 when he steps off the plane, and his velocity increases, and it gets towards 50. And that's when it stops. Well, it doesn't really stop, that's the upper bound for it. And how that works is that this last term here, which varies with e, starts off at 1, which makes it be 0, and then it gradually just goes away, and you're just left with 50 times this initial 1. And now you get to pick some points. So here's your velocity is 50. 1 minus e to minus, what was it, 27 or something like that, 0.27. I can't remember. It's on the other page. If I look back, then I lose everything. All right, t. So put t equals 0 in there. You already did that, and you find what velocity is. So you're really making yourself a little graph. Put the time here, find the velocity. When time is 0, the velocity was 0. And find what happens when t is 5, 10, 15, 20, and 25. And then you graph it. So put the 5 here, put the 5 in this equation, and find out what you've got. And keep going like that. So that's some experience using these exponentials, in a more complicated function. And here's time, and let's see what happens. Here's velocity. Here is the 50. I'm just going to put it in as a dashed line. You'll see it takes, when it starts off at 0, increase your speed rapidly. But then as time goes on, your change in speed becomes less and less until you look like you're coasting into 50, although you never really get there.